Okay, so welcome back to the second module on material balance as applied to iron and steel making processes. So this is the module number 2. So it is recommended that if you have not watched module number 1, it's better that you watch module number 1 before going into module number 2 so that you understand the fundamentals of material balance. So in the first module, we basically said that in a chemical process, which is what happens in iron and steel making processes, basically you need to count the individual atoms which is coming on the input and the output, and this counting can be done either, since it's a large number of atoms, you can basically, it's an order of Avogadro number of atoms, so you use gram moles, or you can correspondingly convert those things into grams or kilograms. So it is possible to do, depending on the convenience, whether one can do it in gram moles, kilogram moles, grams, kilogram, etc. So in the last lecture we said basically one needs to do this elemental balance, looking at individual atoms and making sure that they are balanced as far as the process is concerned. So here I will take up two examples, one from blast furnace, which is a continuous process, assuming a steady state 1, how can one do a material balance, and then on a batch process, basic oxygen furnace. These are the two examples I will illustrate to show how one performs material balance. So let me take up the example of blast furnace. So here I have taken example 2 because I have discussed example 1 in the previous module 1 lecture. So example 2, where one can do an overall balance in a blast furnace. Of course, here to illustrate I have taken a much simplified example where the raw material considered, etc., is much more purer, but in the actual case there can be much more than what I listed, but the basic principles of material balance is going to be the same. So the example says a blast furnace operates with a coke rate of 500 kg per ton of hot metal. Generally this is the way the coke rate is expressed: per ton of hot metal, how much fuel is being used, and it uses 1200 normometer cube of dry air per ton of hot metal. And from the top you also need to charge iron ore, and let us say it contains 95% Fe2O3 and the rest is gangue. The coke contains 85% carbon and the remaining goes to the slag. The hot metal contains 4.5% carbon, that is the product. So calculate the composition of the top gas and the amount of slag per ton of hot metal. So this I have illustrated with the input output, with a box in between, as you can see. So at the beginning you have ore 95% Fe2O3 and the rest is gangue, coke 85% and the rest is gangue, and you have dry blast which is air, which contains 21% oxygen and the rest 79% by volume nitrogen. On the output side, you have hot metal, 4.5% carbon, and the rest is iron, because this is again a simplified case. In principle, there can be other elements like silicon, manganese, etc. on the hot metal, but here, for simplicity, I have taken it as, just carbon and iron. And of course, whatever slag which is there in the ore, as well as whatever gangue which is there in the ore, as well as coke, it goes to the slag. Again, this is not true in the actual case, because some amount of gangue can get reduced, like SiO2 or MnO, etc., and they go to hot metal, and only the rest comes to the slag. But here again we have taken a simplified case, and the top gas contains, of course, CO, CO2 and N2, because in the actual blast furnace it is not only carbon which will be there, there will be also hydrogen, so you will have H2 and H2 coming out of the blast furnace. So again we have to define a basis to start with. So one of the bases which plant uses is per ton of the product. So here the product is hot metal, so 1 ton of hot metal. And what has been given is, we know how much amount of per ton of hot metal which is given on the product side. You can see that 1 ton is already put in yellow, and corresponding to that we have given 500 kg of coke and 1200 meter cube of dry blast. These are the input, and per ton of hot metal product, these are the input which is being charged. So doing a material balance, you need to find out how much ore you need to charge, how much slag will be produced, and what will be the top gas, and what will be its composition in terms of CO, CO2 and N2. So here, if you look at, we have basically elements like iron, oxygen, carbon, of course gangue as one chunk has been put in, because in the simplified problem all the gangue goes to the slag. So irrespective of what the gangue contains, it doesn't matter, all those things goes to the slag. So we need to do the balance of all these individual elements or entities. So we need to start with somewhere, for example, iron balance or carbon balance, oxygen balance, nitrogen balance, and the rest is the gangue balance. So we need to do these balances and see what is the unknown, and whether we can find out this from these balances, whether is it possible to find out the unknown ones. Of course, usually they all will form a simultaneous equation. So you can also write in the form of a matrix and try to see whether you have the number of unknowns matching with the number of equations, and then you can use a simultaneous equation solver to solve it. Again, so it can be a linear one, or sometimes if product comes into the picture, it can become non-linear as well. So here, since it's a much simplified problem, you will see that we'll be able to actually solve one by one and get each of the entities which we want, each of the unknowns which we want. So obviously we are talking about iron. That's one of the main components. So let us start with an iron balance. So if you look at iron balance, of course, since it's a steady state process, it's a continuous process, iron which is there in the input should be equal to iron in the output. In case of blast furnace, since the conditions are so reducing that actually there won't be any slag or almost negligible amount of slag iron oxide in the slag. So all the iron oxide goes into the metal. If that is the case, whatever is the output iron which comes through the hot metal has to be the amount of iron which needs to be charged through the iron ore. So hence, again, as I told you, it can be done in kgs or moles or kilomoles, etc. So let us do it as in kilomoles. So if you look at, we have taken 1000 kg of metal, 1 ton of metal as our basis. So since it contains 4.5%, the rest 95.5% is the iron there. So then converting that kg into kilogram moles, you have to divide by the atomic weight of iron, which is 55.85, so you get 17.1 kilomoles. That means, as I told you, this multiplied by Avogadro number multiplied by 10 to the power of 3 will give you the number of molecules of iron. So now you need 2 molecules of iron to produce one molecule of Fe2O3. So in other words, if I have 17.1 kilomoles, I need 8.55, the half of that Fe2O3 to produce that much. So hence you can see that it's basically 8.55 kilomoles of Fe2O3, and then again multiplying that with the atomic weight of Fe2O3, you can see that it is 1365.4 kgs of Fe2O3. Of course, again, you know that it's not that the ore contains only Fe2O3, it also contains some gangue. So 95% is the Fe2O3, so the rest has to be the gangue. So dividing this 1365.4 by 0.95, you will get 1437.3 kg of iron ore. So by doing iron balance, actually one could calculate what is the amount of ore which needs to be charged. So next, the most important thing is oxygen balance. So let us count in terms of moles, and let us do it in terms of O. So O in the input should be equal to O in the output. That's what is represented there as NO in number of moles or kilomoles should be equal to number of moles in the output. And if you look at, there are oxygen comes through 2 sources. One is air, which we fed into the blast, and the other one is of course the oxygen which is there in the iron oxide. Of course, if there is some other reduction, for example SiO2, MnO, etc., those oxygen also need to be accounted for, but for the present example these are not being considered, so only you have air and Fe2O3. And on the product side, all the gangue goes to the slag, so there is no as such oxygen added from anywhere to the slag. So all the oxygen which goes means which participates in the reaction, they all become either CO or CO2. So hence all the oxygen goes there, which is the output NOCO plus NOCO2. That means number of moles of oxygen in CO plus number of moles of oxygen in CO2. So now we need to find out each of them. So if you look at the input side, we know that the air has O2 in it. So every O2 can give 2 O molecules. So it will give twice the number of moles of O2 in air. which again we can find out because we know 1200 and we know 21% by volume. And then in the last module I was telling you that basically 1 kilogram mole occupies 22.4 normal meter cubed. So from there it is possible to calculate the number of moles of O which is coming through air, which is 22.5 kilomoles. And of course this plus whatever is the oxygen which is added through Fe2O3, which should be thrice the number of moles of Fe2O3, because one Fe2O3 contains 3 O. So hence we already calculated 8.55 moles of Fe2O3 kilomoles. So correspondingly 25.65. So hence total it is going to be 22.5 plus 25.65 is going to be the total number of moles of oxygen which is fed into the furnace. And this should be equal to the output, which contains CO and CO2. And as you know, 1 mole of CO, again 1 molecule of CO needs 1 molecule of O, and on the other hand, to produce 1 molecule of CO2 you need 2 moles of O. That's why the number of moles of O in the output should be equal to NCO, because every mole of CO gives 1, and every mole of CO2 you need 2 moles of O, 2 molecules of or atoms of O, so twice NCO2. So hence our balance should be, the output is NCO plus NCO2. This should be equal to the input NO in, which is NO in air plus NO in Fe2O3. And as you can see, now we don't know NCO and NCO2 because we have 2 unknowns. So we won't be able to solve this unless we have another equation. Then one needs to actually solve it simultaneously. So the next important one is the carbon. So let us do the carbon balance. Again, the carbon enters basically through coke. And we know the composition of a coke, and it's already been mentioned. 500 kg of coke is being charged, which contains 85% carbon, and converting into number of moles you will get 35.42 kilomoles of carbon. And this carbon goes into the gas as CO or CO2, plus there is also carbon which goes into the hot metal has dissolved the carbon. That's what is output as far as carbon is concerned. And 1 mole of CO will contain 1 mole of carbon it needs. Similarly, 1 mole of CO2 needs 1 mole of carbon. So hence the output has to be number of moles of total carbon, which has to be number of moles of carbon monoxide plus number of moles of carbon dioxide, plus for 1 ton 45 kilograms of carbon is being dissolved. So correspondingly dividing by 12 you will get the total number of moles, kilomoles of carbon which is going into the hot metal. So now we have one equation from oxygen balance which we saw, NCO plus 2 NCO2. This is the total number of O which is coming in. The output should be the total number of O which is added, and which we saw the oxygen in air plus oxygen O in Fe2O3 together 48.15, and we know the amount of carbon charge, so NCO plus NCO2, the carbon balance gives you 31.67. So solving these two, one can get what is the amount of CO2 and what is the amount of CO. Because here if you look at in the present case, the amount of CO2 seems to be a bit larger than CO. Actually it shows a very good efficiency, or maybe too good efficiency, which may not be existing in the actual furnace. So maybe the 500 kg of carbon which I gave is not sufficient. One needs to add some more carbon if or carbon in the other forms like coal, etc., needs to be added, then only one can get, then one will get the CO2 almost in the same range. Here actually CO2 is bit more, which is generally, it's too optimistic to obtain. So hence the whole thing has been, now we have solved the whole thing, and of course we also need to find out the gang. So everything can be expressed in the form of table as well, or in the form of this input output balance. As you can see, all those things I have summarized, and you can see that whatever is the gang which is there in the iron ore, as well as whatever is the gang which is there in the coke, together it goes to the slag, and that's where this total slag weight has been calculated. And of course, whatever input per ton of hot metal has to be balanced with the input output per ton of hot metal. So you can see that if you add the total input in kgs, whatever is there, plus kgs on the output, they both of them are same. So you please note that I have converted the moles into kilograms by multiplying by corresponding atomic weights. Again, one can express all these balances in a nice table. So here you can see the input ore, coke, dry blast, and output hot metal, slag, gas, and then I have put all the entities or species: O2, CO, CO2, N2, carbon, gang, F2O3, all those things. And you can see that, I have made the balance, and you can see that it's like a balance sheet. It is like a, accountant when he makes the, whatever is the earnings, as liabilities, asset, those kinds of, he has to do a balance, profit, etc. The same thing we are doing here. Only thing is we are expressing in terms of different species. At the end, whatever is the input side has to be same as the output side if the operation is steady state. Because this is also very useful. For example, if there is a misbalance, if there is a rather, then one needs to look at carefully. First of all, is the imbalance coming out of, there are always errors associated with the measurement. So is it because of that? If it is because of that, then you know that the error is insignificant, so you can neglect it, or you need to improve the way you measure things. But if you find that no, if it is much beyond the measurement error, that means there is some leakage, or there are something which you are not accounted for. For example, here what we have not accounted is dust. After a blast furnace, it does operate with a lot of coke, iron ore, which contains a lot of dust. So a lot of things will go out through the dust. So if you don't account for it, or in a way you can back calculate, if you are not able to account through measurements, you can estimate how much actually dust is getting lost. So one needs to look at these balances in a more critical manner to actually assess how the performance of the processes or the blast furnaces, and based on that one can actually take remedial actions. So that way these balance sheets are quite helpful. Like for a company, it gives the financial status, economic status of the company. Same way, this overall balance does tell a lot of things about the furnace or the process, and based on that you will be able to take some remedial actions so that the performance of the furnace can be improved. So this is as far as blast furnace is concerned. So you can apply this at different levels. There is a model for blast furnace which is known as the wrist model, which in some later lectures we'll be talking about. there you will see that the same material balance along with heat balance is carried out to actually predict what is the fuel rate for or coke rate for a blast furnace. The best coke rate one can achieve for a given raw material input can be predicted. For that, again, the furnace is split into two, and then one applies the material balance across these two, reactors or batch reactors, or you apply this across these two reactors, and based on that you will be able to get the minimum coke rate and the blast rate required. That we will talk about it later. So now let me come to the example of basic oxygen furnace, which is a batch process, as I told you. Here the hot metal which comes from the blast furnace, it contains a lot of impurities, so now you oxidize those impurities by supersonic oxygen jets. So it oxidizes, for example, the carbon to CO, basically primarily to CO, and some amount of CO2 also will be generated, which goes to the gas phase. Then other minor elements, silicon, for example, will become SiO2 and goes to the slag phase, phosphorus, manganese, etc. Of course, inevitably there will be some iron also which get oxidized and goes to the slag phase. And the quality of the hot metal depends on the slag, or what is the composition of the slag. And to control the composition in terms of fluidity and other properties, like you should be able to absorb these oxides quite well. You need to add some fluxing agents. For example, COA is one of the important fluxing agent which is added, and that forms a slag, and generally the slag is characterized by the amount of CaO versus ratio of CaO to SiO2, which is called the basicity, which is used to characterize the slag, and the amount of CaO which needs to be added into the slag into the BOF process is predetermined using the desired basicity at the end of the process, as you will see from the example. So let us take an example from basic oxygen furnace. Again, things are simplified here. So as I told you, this is a BOF operation. It's a batch process, and actually this problem is set by Professor Balal, my colleague at IIT Bombay. So again, it's a simplified problem. So we are having at the input hot metal, where carbon is 4.3%, which is maybe coming from blast furnace, manganese 1, silicon 0.7, phosphorus and sulfur. Of course, whenever, as I told you, whenever we represent percentages for condensed phases, it is basically by default it is the weight percent. And then lime, let us assume that it's 100% CaO, and we have oxygen, pure oxygen being injected through supersonic nozzle, and the output are liquid steel, and we know what is the desired or targeted liquid steel composition. As you can see here, it has to go from 4.3 to 0.08. Manganese has to be reduced. Silicon, almost it becomes nil because silicon can be very easily oxidized. Phosphorus and sulfur, not much can be achieved because sulfur needs reducing condition, and as far as basic BOF process is concerned, it's oxidizing condition, so it's quite difficult to remove sulfur. And the slag, of course, we want to maintain a basicity of 3.5 CaO by SiO2, so correspondingly the CO has to be charged. then how much MnO will be formed, how much SiO2 will be formed, and the P2O5 FeO. We know that the composition wise SiO2 percentage is 15 from the slag analysis, and it contains FeO 15%. And again, gas is concerned, it's 90% CO, and CO2 is the rest. So again, when it comes to gases, as I told you, it is volume basis. So we need to find out how much oxygen is required per ton of hot metal. So let us take 1000 kg of hot metal as our basis. So again, we need to do these elemental balances. So CO is there, CO2, FeO, MnO, all those things are there. So we need to perform elemental balance of carbon, oxygen, iron, manganese, silicon, etc. All those things need to be done. So let us start with iron balance. So we have iron in the input, basically hot metal, we know from the composition, so it comes out to be 937.8 kg, and the output we have iron in the steel plus iron in the slag. So now the problem is, we don't know the percentage of we know the percentage of FeO in the slag, but we don't know the weight of slag. So and we also don't know the amount of liquid steel produced, so hence we have two unknowns, so we won't be able to, we have two unknowns and we have only one equation. So let us try out, for example, the silicon, because silicon, if you look at all the silicon which from the metal goes to the slag. So maybe one can start with silicon, and if you look at, of course, we know the input silicon, and all the silicon goes to the slag, and the percentage of silicon in the slag, SiO2 in the slag, has been given. So by performing the silicon balance, which is the input silicon, again you know that 1 mole of silicon will produce 1 mole of SiO2. So you can see that I have actually converted 7 kg of silicon which is there in the hot metal, and which corresponds to 7 by 28 kilomoles of silicon, and that much moles of SiO2 should be there. Convert that again into weight of SiO2 by multiplying by atomic weight of SiO2, which comes to 15 kg of SiO2, and if 15% SiO2 has to be there, that will give us 100 kg of slag. So now we can put back in the iron balance, and from there you will be able to calculate the weight of liquid steel from the iron balance, which comes out to be 930.05. And we also know that to oxidize iron, we need, so much FeO has gone into the slag, so correspondingly we know 1 mole of FeO is 1 mole of Fe it needs and 1 mole of O it needs, so we can calculate what is the amount of oxygen needed to oxidize iron, which will be 3.34. Similarly for silicon, again the oxygen required can be calculated. Basically oxygen is getting into, distributed to all these reactions, so at the end when we do the oxygen balance, we have to add all these things together. That's why I am accounting for the oxygen which is being used to oxidize in each of these elements. And similarly one can do a Mn balance, so I won't go into the details, but you can go through it in detail, and phosphorus balance, and at the end the carbon balance. So from there one can find out, the oxygen which goes for each of this reaction. And again when it comes to carbon balance, you know that you need to do a carbon balance as well as an oxygen balance, and one can very easily perform all those things, and one knows how much amount of oxygen is required to produce, carbon 90% carbon monoxide and 10% carbon dioxide by volume. So those details you can see it in the calculations, where moles to kgs, all those things have been done. So this one needs to be careful. Quite often you need to convert from one to another, so that sometimes you start counting and then you go back to the kg when you do the actual balance. So now once we know all the oxygen which is needed in the input, that has to be the oxygen which is there in the output. So add all the oxygen for silicon, manganese, phosphorus, iron, carbon together. So that is what is the total oxygen required, which comes to 78.15 kg of oxygen. And that much oxygen now you need to inject through the lances or the supersonic jet, which comes out to be 54.7 nanometer of oxygen. And one can also, based on the basicity, since 15 kg of SiO2 and you want CO by SiO2 to be 3.5, so which corresponds to 52.5 kg. So all these things can be represented again in the form of nice table. Of course, the table looks quite large. When the number of entities in the system becomes more and more, of course this table becomes large, and one needs to do a very meticulous job of like an accountant does. And as I told you, these tables can be studied to understand how, is there anything which you are not accounted for? If that is not accounted, is it significant, or is there any measurements which you make are erroneous? All those information can be got out of these material balance tables. So these are very important tools to look at the process. Rather, the first thing when you want to look at a process is to look at such kind of a table and look for some inconsistencies and all those things. Based on that, one can understand the process in a better fashion. So with this, let me stop here. But I would like to tell you that material balance is only one aspect. Once you do the material balance, there will also be associated energy balance, basically heat energy, which needs to be again balanced. The basic principle of balance is the same. So that also needs to be done, and that is what gives the overall understanding of the process. So that the process can be modified, or any modification you do, how temperature, all those things are going to get affected. All those things can be got out of this material and energy balance. So in the next lecture or module, we will talk about how to perform heat balance for processes which are iron and steel making processes. Thank you.